Yeah, so here we go with classification now on data streams. So we'll have a short introduction in this podcast to the classification problem in data streams. We'll talk about how to train classifiers and stuff like that. And then we'll have a look on two examples of streaming classifiers. One is based, or several approaches actually are based on decision trees. So we'll have a look on those approaches, and we'll have a look on how to use naive Bayes also for data streams. But as I said before, we start with an introduction. So just to recall, I think we can do that quickly. The classification task is to learn from already classified data, so already labeled data. We have the training data, and we want to learn the rules to classify new objects based on the characteristics of the training data. And the result attribute, the class variable, the target variable, is typically categorical. In that is the difference to regression, where the target variable is typically numerical. And here is an example. So we have a set of objects here: screws, nails, paper clips. Those are the training sets, the training data, and we want to learn a rule saying that, for example, right to this line here, everything is a screw, and left to this line, above this line here, everything is a paper clip, and in this area here, everything is a nail. So new objects like these gray objects here can be classified if we don't know the label yet. Yeah, the best batch classification process typically has two steps. So we first train the model, so we learn the model from the training data in the first step, and then in the second step we do the prediction on previously unseen data in order to get the labels predicted. Yeah, and so far we have only considered classification models or classifiers for the batch scenario. So in that case, the whole training data set is given as input of the algorithm, and we can use or access this whole training set multiple times, or an arbitrary number of times during the model generation. Yeah? The model itself is static, so it doesn't change, and when the performance of the model drops, we typically generate a new model from scratch over some new training set we have to determine after a given time period. Yeah, so this is the typical batch scenario, and we have to overcome these basically three limitations here. Yeah, so in dynamic environments, obviously, data changes continuously even. So the batch model regeneration here, the third part here, this batch regeneration of the model is not appropriate anymore. Yeah, and we need algorithms that have the ability to incorporate new data into the training, deal with non-stationary data generating processes. So if the data changes, also the concepts, the classes may change. So we talk about concept drift here, and we have to also probably be able to remove obsolete data. So we probably have to implement some kind of data aging or something like that. The new algorithms should also be subject to resource constraints, so processing time should be minimal, memory consumption should be minimal. In the best case, we have this one-shot, one-look fashioned algorithms. And finally, those algorithms should only use a single scan of the data. As I said before, one look, one shot, no random access. Okay, so let's first talk about non-stationary data distribution. What does that mean in terms of training and especially learning concepts? Yeah, so in a changing environment, a dynamically changing environment, the data distribution may change over time, and the possible consequence, we talked about that, is a change also of the concepts, which we call the classes, the patterns, which we call concept drift. And there may be different forms of change, so the input data characteristics might change over time, but also the relationship between the input data and the target variable might change over time. Yeah, so these are basically two different things. So the latter may possibly is that given, so if we look at the joint probability distribution, intuitively formalizing the relationship between an instance xy and a class at a given time slot, the concept between the concept drift between two timestamps can be defined or formalized as follows here. So the probability or the relationship between xy and the class, the target variable, changes from one time slot to the next time slot. Yeah, so that is actually the concept drift. And if we apply a kind of Bayesian view on the whole thing, well, we know from the Bayes classifier, from Bayesian decision theory, the probability to take class y given a specific observation can be computed by the prior probability of the class p of y, the probability that xy is there given a specific class y. So the probability that we observe xy given that we are so to say in the class y, divided by the posterior, the conditional probability. No, I'm sorry, the probability of the observation xy. That's what the denominator is here. Yeah, p of xy. Yeah, and changes, concept drifts, changes in the data can have impact on all those, basically all those three things here, leading to different posterior probabilities, which we are interested in to take the decision. Yeah? So the prior probabilities of the classes may change. We'll have a look on the next slide about that. The class conditional probabilities, those here, may change. So the probability that I observe something for a given class y can change, and also as a consequence, the decision, the important probability that I take y given an observation x, the posterior probability may also change. And if this one changes here, then we have a real concept drift, because we will decide differently than before. Yeah, because this is the probability we base our decision on, and if this probability changes, we might do a different decision as before. Yeah, so what about, well, having a closer look at those possible changes, different changes here. So first one, the prior probabilities of the classes. So the class probability might change over time. For example, if you have a look at Twitter sentiment data here, we have 1,600,000 instances split in 67 chunks, each of 25,000 tweets per chunk. The whole thing is balanced, 800 positive, 800 negative tweets, but the distribution of the classes changes over time. So you can see the data set online here, following this link, and you see here that the class balance is more or less 50%, not really 50%, but at least stable. And all of a sudden, so here the green ones are the positive, the tweets with positive sentiment. The red ones are the tweets with negative sentiment. So positive, negative is the target value variable, and you see that the probability to have negative tweets is slightly smaller than having positive tweets, but it remains stable. The distribution between negative and positive remains more or less stable over time until here. In this chunk, all of a sudden, from this chunk on, all of a sudden we only have negative tweets. Yeah, because overall we have a 50-50 balanced data set, and since we have a little bit more greens, positives here, we have to somehow even it up for the whole balance. So from here, on all over in those chunks only negative tweets show up. So yeah, the distribution for the negative variable is much higher in that case than for the positives one. Yeah? So that may happen, obviously, and that obviously will somehow impact the computation of the posterior probability which we will take for doing a decision.